Okay, welcome everyone. Thank you for attending today and uh, allowing me to share what's really one of my passions, asphalt. Um, and I've titled this presentation, The Road to Prosperity. But as you can maybe see from this slide, why is it that whenever we start talking about asphalt, people generally gravitate to talking about potholes and all the work that has to be done during construction season in order to to make things happen and provide the roads that municipalities and provinces want to do. So it feels more maybe like the road to ruin rather than the road to prosperity. And I think what I want to be able to do today is show you that with a bit of knowledge and understanding of what's going on out there, we truly can live the line of prosperity, and it would be truly a great thing for this country. So, I mean, any discussion about prosperity has to talk about pavement longevity, right? I mean, because I think this is part of the problem that we're addressing, is that we see roads not necessarily lasting as long as they should, and we're putting too much money into that kind of infrastructure. It creates all kinds of problems, traffic, and more greenhouse gas emissions for that matter, when you think about the construction work itself. So, I mean, longevity has to be talked about. And my colleague, Dr. Hesp, has reminded me that, yeah, 16 years is good for pavement, but you should really be thinking about 30 years, because that's what's possible when you have roads that contain the right material and are laid properly. So, but as you can see from these two photos, that it's not a done deal. I mean, this was a side-by-side comparison, and the thing that is mainly different about the two pavements that have been shown is the asphalt cement that's being used. Okay, so so it really is a match made in heaven. It could be. If you think about what the world needs, it needs more high quality and longer lasting asphalt. And Ontario is included in that, by the way. What do we actually have? Well, we have a resource. Western Canadian heavy crude and bitumen make some of the best asphalts in the world. And there's lots of it, lots of bitumen, that is. So the other thing is, you're probably aware, I mean, we believe fossil fuel demand in North America has peaked, and it's on the way down. And of course, as more and more electric vehicles start populating the roads, what we're going to see is reduced crude running in North America. So if we have reduced the amount of crude that we're going to process for fuels reasons, the problem might be that we won't make enough high quality asphalt, because we really won't have the opportunity to choose asphalt that crudes and to make as much as we need. So that could be an imbalance in the market. The other thing about fossil fuels and making it from oil sands bitumen is that the carbon intensity is very high. We know that. We've been reminded of that many times. But the good news is that the carbon intensity of making asphalt from oil sands is much lower. And I'm going to show a little bit of that a little later on in the presentation. But first, a couple words about definition. When we talk about asphalt binder or asphalt cement, often what I've done in this presentation is shortened it to asphalt. Okay, so if you allow me to do that. And, we have a description of what it is, what it looks like. It's primarily used for road construction, et cetera, et cetera. The second word is bitumen. And, in most countries in the world, if the word bitumen and asphalt would be synonymous, because that's the way they refer to it. Not so in this country. And I take the liberty here to say that bitumen, we're going to continue to define it as the material that we extract from the oil sands formation, whether it's by surface mining or in situ or whatever the case may be. Okay, and often, of course, we add diluent to that to make it flow better, but the bitumen is the material that we often consider the starting point for making asphalt. And then asphalt pavement, well, by putting the word pavement behind it, we're talking about the combination mix of asphalt binder, the stone, the sand aggregate, additives. And what we do is, of course, lay it in courses on the roads, layers, and we build up the necessary strength and elasticity properties needed. And the other thing I wanted to add about asphalt pavement is, believe it or not, it's only 4 to 5% asphalt binder. So there's not a lot of it. Yet its performance properties are important to overall road life, because really it's the glue that holds everything else in place. Okay. So making asphalt from crude oil or bitumen. Most important thing, if there's one thing you take away from today, is that you got to have the right molecules in the feed. And so that's the only way you'll make high quality asphalt. Well, what is that, the high qualities? Well, a lot of times we talk about asphaltenes, and that's a family of compounds, very complex family of compounds. But it's got to be the right amount of asphaltenes and the resins that often just keep it well dispersed. Because what you're really doing is trading off stiffness for ductility here. In other words, if I went and put bitumen through a solvent deasphalting process, it might not necessarily make the best asphalt in the world, because you might have too much concentration of asphaltenes and you'd have a material that would be stiff, and it would probably be more prone to cracking, et cetera, et cetera. Some of the other things I want to mention about asphalt and making the right stuff: should be low volatility, because it has to prevent flash issues. And not only that, but people working on roads being in contact with it, you want a low amount of volatile material for that purposes, for exposure purposes. And you also need a material that provides resistance to different failure modes. There are failure modes for asphalt that are at low temperature, and then there are failure modes for asphalt at high temperature and different aging conditions. So you want to be able to have the right combination of molecules to be able to address both. So conventional processing, it uses the atmospheric and vacuum distillation processes that you see in many refineries. And that's there to separate the good from the other stuff. So this is what I call the cartel. And the cartel is 4 families. Now, these 4 families are, if I had a beaker of asphalt here in front of you, those 4 families are shown, right? You've got the asphaltenes, the very highly complex molecules, often dispersed by the resin phase. And then you have aromatics. And even in asphalt samples, you have some degree of saturates as well. And so these are the 4 very different types of molecules that form the family. Now, a couple of things I wanted to mention before we get into it is really about how do you make a softer or a harder asphalt. And really, this is a bit of distillation 101 to start. So if I have, in this case, a diluted bitumen, it's called AWB, Access Western Blend, and I have a true boiling point curve for it. What it shows is, as you go up in percent off, as you distill more and more of that sample, the temperature rises. So these are various components of AWB that are distilled, and the blue line would be the relationship between percent off and temperature. Now, unfortunately, the world is not a perfect place. And so if you try to distill this in a atmospheric, or both an atmospheric and a vacuum distillation column, the four materials shown here, the diluent being the lightest, the AGO, atmospheric gas oil, next, vacuum gas oil next, and the heaviest being asphalt, what you'd actually see is that the diluent, for example, would have a longer tail on the back end. The AGO would have a lighter front end than just sitting on this blue curve. The AGO would have a tail in the back end, and the VGO would have a lighter front end, and so forth. So those are the imperfections of distillation today, and how you actually separate different streams. Now, in order to control this softness or hardness of asphalt, what you're really talking about doing is raising or lowering the temperature which you process or pull this material off the column. And what it means is, if you wanted to make a harder asphalt, for example, what you would do is you'd raise the temperature and pull those molecules into the VGO that were in the front end of the asphalt. If you wanted to make a softer asphalt, you do the reverse. You basically drop temperature, allow some of those VGO molecules to enter the front end of the asphalt. So that's really important to understanding how we would change the asphalt grade, perhaps, or make the material a certain PG grade. So any crystal clear will hopefully. So let's talk a little bit about SuperPave PG grading, performance grading system. Whoops. SuperPave, prior to SuperPave, in the beginning, there was penetration test, right? And the penetration test from CGSB, the Canadian Governing Standards Board, was really a measurement of physical properties of the asphalt. Now that's a good start, but the thing is, when you're talking about measuring the performance of the asphalt, it's better if you can measure them directly in terms of what they're going to do in the field. Okay, so that's what we do now with the SuperPave PG grading system, is we have tests that are more relatable to what the asphalt's going to see in terms of services. And so it's things like the stresses and strains of the binder and how they behave to various tests with rheometer and so forth, that both at low temperature and at high temperature, because both can affect the failure mode. So PG grading is really about that, is finding the limits to high temperature and the limits to low temperature under which this asphalt will perform. And the example shown at the bottom, PG 58 minus 28, that means that this asphalt is suitable for an average 7-day maximum pavement design temperature of 58 degrees C. And on the low temperature side, the minus 28 value refers to the minimum design temperature. So this would be how you interpret PG grading. And of course, it's going to be a property of other things besides the temperature. And so on this graph here, what you can see is it's just like I was talking in the beginning. It's about the crude more than anything else. And so often what we do with PG grading is we plot the low temperature characteristics along the bottom and the high temperature characteristics along the vertical axis. And really, it's a signature of the crude. So what we're showing here are three different lines: crude A, crude B, and crude C. And what you'll notice is that there's a box. For example, let's talk about PG 58 minus 28 again. There's a box there, and crudes A and crudes B, depending on how you're distilling them, can intersect that box. And when it intersects that box, it means you can make those grades from those crudes. But notice how crude C cannot intersect that box. So you can try all day to try to come up with a distillation that will do it, but you just won't get there. So that's why, again, we say it's all about the feed and what the crude is. Okay, let's see, anything else I need to mention here? Okay, try to get this thing going again. Here we go. So very important. We've just talked a little bit about PG grading, and you can see, if we have a PG 58 minus 28, what does that mean? Does that tell us anything about pavement longevity? Well, guess what? The sad news is that you can make a PG 58 minus 28 that won't necessarily last, won't have pavement longevity, even though it'll make the initial specs for PG 58 minus 28. And that's because there are certain practices that can be problematic. For example, if I take this bitumen and distill it to make PG 58 minus 28, but I decide that I'm going to distill it much deeper and I'm at a much higher temperature, I could make a very hard asphalt, could be a PG 70 or whatnot, and then I could blend back into it something which we call a softening agent. And generally, softening agents have been problematic in that for whatever reason, the molecules may not be entirely compatible. And so you can meet all the specs, the PG specs for a given service, but you may find that that material doesn't last. And so what do you do if the PG system itself can't tell you everything you need to know? Well, luckily, and I know Dr. Hesp had been involved extensively in this, we have other tests. One is called the Extended Bending Beam Rheometer, EBBR. And really, it is very much like the bending beam rheometer, which we use now to determine low temperature properties. But it's cold conditioned much longer. And by doing that, you'll find that it'll give you a better idea of what the susceptibility of that asphalt is going to be to low temperature cracking. So the EBBR has become a very useful test. And the other test that's useful is the double-edged notch tension test. And the intent here is to actually measure what the resistance to ductile failure will be in the intermediate temperature range. So these are two tests that can help us determine whether or not this asphalt will last. And I'm sure, and there are many others that are used by road builders today. All right, so that's fortunate. Now, I think the last topic we wanted to talk about is greenhouse gas emissions from making asphalt. So there's basically three things I wanted to cover here. First one is about the trends we are seeing. Will governments, for example, like Ministry of Transportation Ontario, will they care? Will road builders care about greenhouse gas emissions and carbon intensity? The other thing I want to do is spend a few minutes just reviewing what scope 1, 2, and 3 emissions are and how they might relate to asphalt. And I also wanted to do a bit of a comparison between asphalt emissions and fossil fuel emissions, both of them coming from bitumen. So just to cover the trends, I think pretty well everybody out there that's big in the asphalt business would say there's no premium yet that green asphalt, if there's such a thing, can demand in the marketplace. There is a lot of provincial jurisdictions that are seeing pressure to buy green, and I guess many of the suppliers are concerned about will those contracts be awarded based on emissions or not. So we're not seeing anything there yet. In the US, there's some interesting developments. One is about EPDs, environmental product declarations. So there's an effort by NAPA to provide some product category rules for that. But basically what that will do is allow an asphalt supplier to make claims about how their products perform in an environmental way. So that's, I think there's more of that coming. And also the Asphalt Institute recently has published some data around global warming potential, and they've included a number of steps through the whole value chain, all the way from the upstream through refining and through transportation, marketing, terminaling, and so forth. So the fact that these two organizations are getting in gear on this tells us that they're treating it seriously. And the feedback we're hearing from large road builders on both sides of the border is we're getting prepared with both suppliers and the customers, so both ends. So a little bit of a refresher on emissions classification. I'm going to talk a little bit about scope 1, scope 2 emissions, and scope 3. Scope 1 and 2, you're probably more familiar with that. Scope 1 is all about direct emissions. So if I have a facility, say it's making asphalt or separating asphalt from the rest of a crude barrel, they're direct emissions, and so they're from owned and controlled sources. So for example, I might have a gas-fired heater at my site, and so I am burning fuel gas, maybe some natural gas, maybe even fuel oil if it were an old facility. It's really the energy required for asphalt. It's applied to the asphalt separation process and to tank heating. Okay. Now, scope 2 emissions, there are more indirect emissions, usually from generation of purchased energy. In our case, we see that a lot in terms of electricity. So the manufacturing of asphalt, there's electricity associated with pumps, compressors, heat tracing, even electric tank heaters. And that can be electricity purchased over the fence from the grid. And those are considered scope 2 emissions. Now, there will be possibly some trade-off between scope 1 and scope 2. For example, you instead of heating something with fuel gas or natural gas, you could use a different heating media that might be a scope 2 source of energy. Now, scope 3 emissions are the interesting one because it tends to be more a catch-all for a lot of different things. So it's defined as all indirect or value chain emissions, and that includes use of a product. And that becomes very important here when we talk about the comparison I'm going to show you. The emissions for the use of fossil fuel products, in other words, combustion, are very high indeed. We'll show a few numbers. And it's less so for the use of asphalt. Yes, there's some hot mix energy that has to be inputted. There's the road application of pavement. But I think our experience tells us that these are small in comparison to what happens when you burn a fossil fuels product. So here's the comparison. And first, I'll declare that this is not a full analysis, and we can do the analysis many different ways, I'm sure. But what I've tried to do here is do a comparison of emissions. And I've used the undiluted bitumen basis because it, again, helps simplify the analysis, not having to know whether diluent gets consumed and burned or whether it gets recycled back to a producer. So what I've done here is I've looked at fossil fuels and asphalt. And when you look at the scope 1 and 2 manufacturing, first of all, you notice you get a lot more energy inputs required to make finished gasoline and finished diesel from bitumen. And the little diagram on the lower left-hand side shows what we're doing. We're taking a barrel of bitumen and we're sending it through an upgrader. You'll make some coke, you'll make some sulfur, some fuel gas. But generally, most of what you make ultimately will come out as gasoline, diesel, maybe jet fuel. And those components are blended, they're transported, and then they are used. And in almost all cases, they're used as, they are burnt for the fuel value. So that's bitumen to fossil fuels. If you look at bitumen to asphalt, it's a very different story. First of all, if we're using undiluted bitumen, asphalt yield is about 80%, 82 weight percent, 80 volume percent. So that's the where most of it is going to come out. And whoops. Sorry about that. So really, we follow two streams coming out of the asphalt plant. One is a small amount of fuel, because whatever is not made as asphalt is separated, and it is, again, going to be burned. And that's about 20% of the barrel. And the other 80% of the barrel is asphalt, and it sees some other energy inputs, although quite small, through the terminaling and through the hot mix plant to make pavement. So when you look at this, as you can see here, the scope 1 and 2 manufacturing inputs are much higher for the fossil fuels being processed through an upgrader in a refinery than they are through an asphalt plant, where all you're really doing is simple distillation. And if you have a lot of heavy molecules, you don't end up putting a lot of energy into that to get the separation. So that's why we have such a big difference between fossil fuel use and asphalt use for bitumen. Now on the scope 3 side, again, you can see a fair difference for the fossil fuels, much higher at 400 kilograms of CO2 equivalent per barrel of bitumen, and asphalt being much lower because we're burning much less of the bitumen barrel to do it. Okay, so this is, I'm sure there are some other sources of energy inputs along the way that I haven't accounted for here. And the intent here is really just to show you the magnitude of the numbers and how different they can be. So in summary, there's no doubt in my mind that increasing asphalt production from heavy Canadian crudes and bitumen is a big opportunity for Canada. The science of making asphalt is well understood, and with minimal technology risk. Carbon intensity, I hope I've been able to show you that the carbon intensity for making asphalt is lower than fossil fuels, making fossil fuels from bitumen. And we also know that technology is strongly supported by Alberta Innovates and the Alberta government under their BBC mandate. So there's quite a match here between what the Alberta government sees and what we see as the opportunity. So the key here is to put asphalt first. We have to make high quality material, and if we're focused on doing that, then the prosperity will follow. And that's all I have in terms of presentation.